In this lecture, which is the advanced lecture on PCA, we are going to prove that the PCA algorithm actually accomplishes what I said it would previously. Just as a recap, let's remind ourselves of what PCA can do. First, it does dimensionality reduction. We can reduce dimensionality by taking only the most important principal components. This is the same as denoising in visualization, because to do visualization, we need to reduce dimensionality to 2. To do denoising, we remove dimensions, which are just considered noise. So what we actually want to show here is my claim that the Z matrix, which we get back from PCA, will actually be ordered in terms of decreasing variance. As you recall, we use variance as a proxy for information or importance. The second thing we want to prove is that the columns of Z, that is, the principal components, are decorrelated from each other. In other words, their correlation or their covariance should be 0. Okay, so our goal in this lecture is as follows. We're going to derive PCA, and I'm going to show you how the cube matrix we looked at earlier can be found. Furthermore, we're going to show that by using this particular cube matrix, the Z that we get when we transform X to Q will lead to the above properties. These properties, again, are that the principal components will be ordered by variance and they will be decorrelated. Okay, so let's begin. The trick behind PCA is that it's nothing but eigendecomposition. In other words, finding eigenvalues and eigenvectors. So let's remind ourselves about what that means. As we discussed earlier, we said that when you multiply a vector by a matrix, you can potentially do 2 things. First, you'll rotate it so that it points in a different direction. Second, you'll stretch it so that it becomes either longer or shorter. Eigenvalues and eigenvectors are special values in relation to a matrix. Specifically, suppose we have a square matrix called A. Then, if we have some scalar lambda and some vector v that satisfy the equation A times v equals lambda times v, then we call this lambda an eigenvalue, and we call this vector v an eigenvector. Okay, so what's special about the eigenvalue and eigenvector? Well, what this equation is saying is that when we multiply v by the matrix A, this is the same as multiplying v by some constant lambda. But we know that when we multiply a vector by a constant scalar, it doesn't change direction. Yes, if the scalar is negative, then it might reverse direction, but the direction is essentially the same. Thus, the vector only changes in magnitude. So that's what's special about eigenvalues and eigenvectors. Eigenvectors are special vectors that, when you multiply them by A, they are not rotated. Instead, they are only scaled. How much are they scaled by? They are scaled by the value lambda. As a side note, for this lecture and this course, eigenvalues will always be positive, so the eigenvector will not reverse direction. Okay, so what matrix are we actually going to use eigendecomposition on? The answer is the covariance matrix of X. Let's think about what that means. Recall that you've seen the covariance matrix earlier in this course multiple times. So to recap, X is an n by d matrix. In our case, n is the number of dates or time steps in our dataset. D is the number of stalks. We can think of this as n samples of the d-dimensional vector little x. The definition of covariance is the expected value of x minus its mean times the same thing transposed. As you know, we can calculate this practically by using the sample covariance. This just takes the thing inside the expected value for each sample little x sub I. Then we add them all together and divide by n. Also, recall that we can do this calculation in matrix form. And again, remember that there's some abusive notation here, because technically, you cannot subtract a vector from a matrix, but we'll assume it's doing something like NumPy broadcasting. So if you do this in code, it will actually work. Okay, so what do we get after we do this calculation? We get a d by d matrix that we call sigma. Each element of sigma tells us the covariance between each one of the d stalks and each one of the other d stalks. So sigma ij is the covariance between stalk I and stalk j. Note that this matrix is symmetric, so the covariance between stock I and stock J is the same as the covariance between stock J and stock I. Furthermore, note that along the diagonal we have the variance, so the covariance between stock I and itself is just the variance of stock I. Now let's suppose we do eigendecomposition on this covariance matrix of X. What will this give us? Although the details are outside the scope of this course, we will get D unique, non-negative eigenvalues, and D corresponding eigenvectors. For all practical purposes, we can assume that the eigenvectors are positive. There are several important properties of these eigenvectors that we need to discuss. The first property is that they all have length 1. In fact, we can choose this to be the case. Recall that eigenvectors can be scaled arbitrarily. To see this, just consider the eigenequation AV equals lambda v. If we multiply both sides by c, we get a new vector v prime, which is just v scaled by c. Obviously, this also satisfies the eigenequation. So we can conclude that eigenvectors are not unique, and therefore we can freely scale them so that their length is 1. An equivalent way of stating this is that the norm squared is 1, or that v transpose multiplied by v is 1. If you're not convinced that these all mean the same thing, please write this down and work it out as an exercise. The second property is that all the eigenvectors are orthogonal. So what does that mean? Geometrically, you can think of this as each eigenvector being 90 degrees or at right angles relative to all the other eigenvectors. In fact, you saw an example of this already when we looked at the height and weights graph. When we rotated this data, we rotated it in such a way that the new axes, z1 and z2, were still at right angles relative to each other. So what this means is that, after we rotate the data in d-dimensional space, the axes of the new dimensions are still at right angles. Mathematically, what this means is that, if you take two different eigenvectors and calculate the inner product between them, you will get 0. I would recommend that, if you've forgotten this, verify for yourself that if you have two vectors at right angles and you take the inner product, that you will always get 0. Okay, so hopefully you're convinced that this is true. And remember, this is only for eigenvectors that are different. If you take the same eigenvector and dot it with itself, then you will get 1, which is what we discussed on the previous slide. If you want to know why this is true, here's a short proof. Consider the quantity lambda I times v sub I transpose times v sub j. Let's assume that I and j are different, so vi and vj correspond to different eigenvectors. Well, we know that lambda sub I times v sub I is also equal to sigma times v sub I by definition of the eigenvalues and eigenvectors. I've grouped together lambda I and v sub I in brackets to make this more clear. So we can replace lambda sub I with sigma. So I have sigma times v sub I, all transposed, times v sub j. Now remember that, when you take the transpose, the order of multiplication reverses. So this is the same as v sub I transpose times sigma transpose times v sub j. But we know that sigma is symmetric, so sigma transpose is just sigma. Then, we recognize that sigma times v sub j is also an opportunity to plug in an eigenvalue. Specifically, it's just lambda j times v sub j. So we've discovered that lambda sub I times v sub I transpose times v sub j is equal to lambda sub j times v sub I transpose times v sub j. But how can this be? Remember that lambda I and lambda j are different. If they were the same, then they would have the same eigenvectors as well. So the only way that these two expressions can be equal is if the dot product between v sub I and v sub j is 0. And therefore, v sub I and v sub j are orthogonal. Alright, so altogether, if the length of each eigenvector is 1, and each eigenvector is orthogonal with the others, then we can say that they are orthonormal. For reasons which won't be clear yet, what we would like to do is organize these eigenvectors into a matrix. We'll call it big V. So the first column of big V is V1, the first eigenvector. The second column of big V is V2, the second eigenvector, and so on. And we just keep repeating this pattern until we get up to VD. Altogether, this is called an orthonormal matrix. Sometimes people just call this an orthogonal matrix. However, I prefer orthonormal because it explicitly tells us that each vector is orthogonal and has unit length. What is interesting to consider is, what happens if we multiply V by itself? Specifically, what if we take V transpose times V? Well, the first element at row 1, column 1 is V1 dotted with V1. As you know, that's just 1. The second element at row 1, column 2 is V1 dotted with V2. As you know, that's 0. If you finish the rest of these calculations, you'll recognize that the result is the identity matrix. You can do a similar calculation to show that V times V transpose is also identity. So what does this imply? It implies that the transpose of V is also the inverse of V. This is because, by definition, a matrix multiplied by its inverse is identity. Okay, so how do we put this all together? Now I realize this seems like a lot of completely random steps, but it will all make sense very shortly. Well, since we've put all the eigenvectors into a matrix, let's put all the eigenvalues into another matrix. We'll call this capital lambda. It's a diagonal matrix since all the off-diagonal elements are 0. The diagonal of this matrix contains the eigenvalues, lambda 1 up to lambda d. One important thing to remember is that each of the d eigenvalues is just a number. Typically, we use software to solve for eigenvalues and eigenvectors, like NumPy if you're using Python. In school, you'll usually learn how to find these for small matrices, but obviously you can't do that if your matrix is 500 by 500. Okay, so we have d eigenvalues and d eigenvectors that we just got back from NumPy. We organize them into matrices. In fact, when you use NumPy, what you get back is already in this form. But very importantly, we are going to sort these eigenvalues and the corresponding eigenvectors so that they are in descending order. Now the reason why won't be obvious now, but it will make sense in the end. So that's one important fact I want you to remember. Although these eigenvalues are completely arbitrary numbers, we're going to organize them in this big matrix lambda so that they are sorted in descending order. That is to say, from biggest to smallest. So lambda 1 is the biggest, lambda 2 is the second biggest, and so on, and then lambda d is the smallest. Okay, so what's next? Now that we have the eigenvalues and eigenvectors stored in matrices, we can form the eigendecomposition in matrix form. This is written as sigma times big V equal to big V times big lambda. Now, this might look a bit strange, since when we write this in the usual vector form, V is on the right side both times. So as an exercise, what I want you to do is multiply out the matrix form, which will give you back these separate equations in vector form. You should be able to verify that these d separate equations are the usual vector equations for eigendecomposition. In other words, this ordering, sigma times v equals v times lambda, is the correct order. Now, there are two ways that we can rearrange this equation, which might be helpful. First, we can multiply v inverse on the right side. This will give us that sigma is equal to v times lambda times v inverse. We know that v inverse is equal to v transpose, so we can write that down as well. Now you see why this is called eigendecomposition. We have decomposed sigma into two parts. One part is a diagonal matrix of eigenvalues. The other part is an orthogonal matrix of eigenvectors. Another thing we can do is multiply v inverse on the left side. This gives us that lambda is equal to v inverse times sigma times v. And again, we replace v inverse with v transpose. So what does this say? Usually when we do this, we say that we've diagonalized sigma. That is, we found some equivalent representation of sigma in terms of a diagonal matrix lambda. Now again, these might seem like arbitrary curiosities, but they will come together soon. The next step is to remember what we are doing. We are doing PCA, where our job is to find some matrix Q so that we can transform any vector x into a vector of factors called z. We can also do a reverse transformation by using Q again. Well, what is this Q matrix? This Q matrix is just V, the matrix of eigenvectors that we just found. Now that we've done all the groundwork, the rest of this lecture will be easy. All we have to do now is prove that using this choice of Q will lead to the properties of Z that we discussed earlier. Just as a reminder, this is that each column of Z, which is a factor, is ordered so that the most important factors are on the left and the least important factors are on the right. Furthermore, each column of Z is uncorrelated with the others. That is to say, the factors are not redundant. Okay, so next, just as a sort of arbitrary task, let's try to calculate the covariance of Z if we use V as our transformation matrix. We can start with a definition of covariance. We'll denote the covariance of Z by sigma Z. It's the expected value of Z minus the mean of Z multiplied by its transpose. But we recall that Z is just V transpose times X. So we can replace Z with V transpose times X. We can also replace the mean of Z with V transpose times the mean of X. The next step is to factor out the V matrix since it's not a random variable. On the left side, we have V transpose, and on the right side, we have V. But the important part is what we have in the middle. As you can see, it's just the covariance of X. So we can replace that with sigma X. Well, you might recognize this as something we derived earlier. In fact, this is just lambda, the matrix of eigenvalues. So what is this saying? It's saying that the covariance of Z is just the matrix of eigenvalues, where those eigenvalues were derived from X. What does that mean? It means that any of the off-diagonal values of sigma Z are 0, because by definition, lambda is a diagonal matrix. What does that mean? It means that the covariance, and equivalently the correlation between any factor in Z and any other factor in Z is 0. That is to say, the factors in Z are uncorrelated. As you recall, this is one of our claims from earlier. Furthermore, remember that we sort of arbitrarily decided to sort the eigenvalues in descending order. So the eigenvalues are sorted from biggest to smallest. But what do these eigenvalues represent? Well, these are the variances of each factor in Z. So lambda 1 is really the variance of factor 1. Lambda 2 is really the variance of factor 2. Thus, each factor in Z is also sorted in order of descending variance. The variance of factor 1 is the largest, the variance of factor 2 is the second largest, and so forth. And remember that we are using variance as a proxy for information. So the first principal component has the most information, the second principal component has the second most information, and so on. Okay, so that concludes our derivation of principal components analysis. In this lecture, we proved that PCA has the properties we described in the previous lectures, and therefore is suitable for the tasks that we claim that PCA can do. As you recall, these properties were that when we transform the data, the new data is uncorrelated. Furthermore, the columns are ordered in terms of importance, where importance is measured by variance. This allows us to perform dimensionality reduction, visualization, denoising, and decorrelation. And this allows us to build a statistical factor model such that we can choose the most important factors that affect a stock's return and ensure that each of these factors are not redundant.